Indoor mapping is the practice of discovering a closed-off space, such as a room or a floor plan, and designing a virtual map of the discovered space. The discovery robots collect sensory data, such as the speed and acceleration of the vehicle, to estimate the position of the robot with respect to the point of initialization. Indoor mapping technologies are commonly used in industrial spaces, such as warehouses and factories. Due to the rapid rise of smart vacuum cleaners, indoor mapping technologies are also becoming increasingly popular for individual use. The market for indoor localization is estimated to be over $6 billion as of 2020, and the market is expected to almost triple its value by 2025, reaching a total market value of $17 billion. We were inspired by the favorable trend of indoor mapping technologies, so we designed an indoor mapping robot that would autonomously move in an indoor space, mapping the walls of the environment. We initialized our robot to begin discovering the environment by scanning the room for right or front walls. The presence of the walls are detected by the ultrasonic distance sensors facing the front and the right sides of the robot. When the robot discovers a right wall in a threshold distance, it starts cruising by following the wall. If there is no right wall detected, but a front wall is detected, the robot moves closer to the wall and when it reaches the wall, turns left to have the wall on its right. If neither walls are detected, the robot takes a 360 left turn, scanning the room, and if there are still no walls detected, the robot moves forward and repeats the process. After detecting a right wall, the robot starts cruising and updates the distance that is traveled every tenth of a second, with the velocity and acceleration of the robot and the elapsed time. If a front wall is detected, the robot turns left to avoid crashing and to have the front wall placed on its right. Due to the deviation of the robot, we implemented an algorithm that would keep the robot at a fixed distance from the wall, to prevent the robot from straying away from or bumping into the wall. Sharp changes in the right wall distance are recorded to capture the bump-ins or bump-outs from the wall that the robot is following. If the right wall is lost, we ask the robot to take a 360 right turn to find the right wall again. When the discovery is finished, the robot stops and prints the indexes and lengths of each wall, so that the dimensions of the map can be compared to the actual space. By comparing the actual and virtual maps, we can see that the map is highly accurate in shape, and the error margins of wall lengths are low. The map that is created is then converted to a JPEG file and uploaded to a local server through Wi-Fi. From the local server, the application retrieves the image and saves it to the SD card of the Android. When the Display Map button is pressed, the app displays the image from the SD card. Since the application is Wi-Fi based, the robot and the Android phone must be connected to the same Wi-Fi network. Thank you for listening to our final project demonstration.